Good evening, sir. Myself Karan Das from third year EC department. This code is for a perfect demonstration of the Nyquist-Shannon sampling theorem. It visually and mathematically proves what happens when you sample a signal correctly versus when you sample it too slowly, which causes aliasing. Now we are talking about the codes. I will be talking about first this part. We start by importing NumPy for the heavy mathematical lifting and matplotlib for our visualization. We are creating a complex signal out of two sine waves. One is at 50 Hz amplitude 1 and the other one is at 120 Hz amplitude 0.5. Find Find the highest frequency in our signal 120 Hz. The Nyquist rate calculate the absolute minimum speed we need to sample this signal to capture it perfectly. Exactly twice the highest frequency, like 240 Hz. Now I am going to talk about this part. This part explain that computers can't truly create continuous analog signals. To fake an analog signal for our plot, we use a massively high sampling rate. There FP equal to 10,000. Uh, Creates an array of time steps for zero point 0.1 seconds, generates our reference signal by adding the 50 Hz and 120 Hz sine waves together using our dense time axis. Now we are talking about, I will be talking about this part. We define three sampling rate to test safely above our 400 Hz, safely above our 240 Hz Nyquist rate, 240 Hz exactly at the Nyquist rate, and 180 Hz below the Nyquist rate. We also set up a giant plot figure to hold the 15 different plots. We are about to generate 5 plots for each 3 cases. For this part, now I will be telling. We start a for loop to run our 3 test cases. Uh, Ts is the time step between each sample. T underscore is the actual time array for our samples. And x underscore s calculates the exact value of our signal at those specific spread out moments in time. The represent this represent what an analog to digital converter ADC does. Now the next part, this is the most complex math in the script. To turn digital dots back into smooth analog wave, we use sync interpolation, also called ideal band limited interpolation. Tau uses NumPy broadcasting to calculate the time difference between every dense plotting point and every single digital sample. We pass those difference into np.sync first bracket close. Finally, the at symbol performs matrix multiplication, effectively dropping a smooth sync wave onto every digital sample and adding them all together to reveal the original wave. Now this part, we subtract our reveal signal from the original to find the recon error, and the mathematical formula for finding out where a frequency will fold and alias to if we sample it too slowly. If the observed frequency doesn't match our original frequency, the code prints an alert that aliasing has occurred. Now, for plot 1, this is the plot. This plot smooth original wave overlays a stem plot showing exactly where our digital samples were taken. And the plot 2 and the plot 2, this overlaps the original wave with our sync reconstructed wave. In the 400 Hz case, they will overlap perfectly. In the 180 Hz case, they won't match at all. Plot 3, a simple plot of the difference between the original and reconstructed signals. It shows exactly how much data was lost or distorted. Now for the next part, we use fast Fourier transform. Time domain plots are great, but frequency domain shows why aliasing happens. We use np.fft.fft to extract the frequency present in both the original and revealed signal. FFT shift is just a utility that centers our 0 hertz frequency in the middle of the plot, so it's easier to read. And the plot 4 and plot 5, this final plot shows the frequency spikes in the original plot. You will clearly see spikes at the at 50 hertz and 120 hertz. For the 180 hertz test case, when you look at plot 5, you will physically see that the 120 hertz spike has shifted to the wrong location, aliased to 60 hertz, because the sampling rate was too low to capture it accurately. Now we are talking about the graph. Starting with the top row, we safely oversample at 400 hertz because we are well above the Nyquist rate the sync reconstruction plot shows. The sync reconstruction plot shows the reconstructed line perfectly tracing the original waveform. If we check the reconstruction error plot, the error is incredibly small, bouncing just between 0.1 to 0.2, and most importantly, our reconstructed spectrum perfectly matches the peak our original spectrum. This one here. Now, moving to the middle row, we hit exactly 240 Hz, the bare minimum Nyquist boundary. The scene reconstruction still look highly accurate to the human eye. However, if you check the reconstruction error, it has increased compared to the 400 Hz case. Scaling from 0.5 to 0.5, 0.5 to 0.5 to not minus 0.5 to 0.5. Okay, we are right on the edge of the mathematical limit, but our reconstructed spectrum confirms we still successfully captured the correct frequency. Finally, the bottom row shows what happens when we sample at only 180 Hz. This is undersampling, and visually it is a disaster. Look at the sync. Sync reconstruction. The reconstructed wave doesn't match the original signal at all. Our reconstruction error is huge, swinging widely from -1 to 1. But the absolute part is the final graph. The title explicitly says reconstructed allies 60 Hz because we didn't sample first enough. mm, First enough. First enough. The original 120 Hz tone get mathematically folded backward. The system reconstructed a phantom 60 Hz tone that never actually existed in the original signal. That's it. Thank you.